All right. So when you're model building and you want to construct a theory, there's typically rules about how you write the terms down. Right. You normally want to write down terms that are normalizable. Okay. We'll get into that later. Right. But you also want to consider terms that preserve symmetries that that the free field theory or symmetries that you observe in nature in the form of conservation laws. Okay, but today we're going to consider just several theories, and I'm just going to write down the interactions, and we'll talk about the reasons behind them later. Okay, and just a note that to preserve causality, right, we are going to always write down interactions occurring at the same space-time point. Okay. Right, so a term like a phi to the fourth term, where you have a space-time point x, that's fine, right? But if you have some interaction between two fields at space-time point x and space-time point y, that's not good. Okay, so we're not going to worry about terms like that. We're always going to worry about terms that will be at the same space-time point. Okay. Okay, and the way we're going to write these terms is like this. Okay, so we're going to have probably one of these is supposed to be like a curly H. Okay, so we're going to write down. We'll start with the basics, like either the Dirac theory, free theory, or the Klein-Gordon theory, right? Or maybe sometimes both of them. And then another new term that I'll talk about in a minute. But we'll add on some interaction. Okay, and the interaction will be of the normal form. We'll typically write down the theory with using the Lagrangian formalism, but every once in a while we'll use the Hamiltonian. Okay, and another note is that in these terms, we're only going to consider interaction terms that are just functions of the fields. Okay, so they can be functions of multiple fields, like different fields. But we're not going to consider derivative terms. Okay, those do come into play when you get into QCD and other things. Non-ability engaged theories, which we'll touch on at the end of the semester. But for now, we're just going to consider terms that are just built out of the fields themselves. Okay. All right, so in this set of lectures, we're going to consider three types of interacting theories. Okay? The first one is kind of the standard, it's called phi to the fourth theory, or sometimes called lambda phi to the fourth theory. So it's a term, or it's a Lagrangian, a theory that contains the Klein-Gordon piece, the free Klein-Gordon piece, and then you add into it an interaction term that goes like phi to the fourth. Okay, and lambda here is just a small, and it turns out to be dimensionless coupling. Okay, and the fact that it's small is very important for how we go about solving these types of theories. Okay, and you might think, oh, this looks too simple. It's a toy theory, right? But it turns out that there's a very important example of this theory, and it's the self-interactions of the Standard Model Higgs. Okay? So the Higgs, if you look at the Lagrangian for the Standard Model, you'll see this term in there, right? You'll see this Lagrangian, or this piece of the Lagrangian in the Standard Model Lagrangian. Okay? So it's an important example, and we've observed the Higgs. We don't know that it interacts through these terms yet, but that's what they're that's what they're testing now. Okay. All right, so you start with that Lagrangian, and then the first step is always to derive the equations of motion, right? So we did that for the free theory. We derived the equation of motion, and then we were able to solve it. We found it was some retarded Green's function or whatever. Okay, so you can do that same thing for our phi to the fourth theory, and it turns out the equation of motion looks something like that. Okay, and unfortunately, the techniques that we apply to the free theory are not applicable here. Okay, so you can't do the Fourier analysis. You can't expand. the things that you would normally do to solve the theory, you can't do that here. Okay. All right. So that's one theory that we'll talk about. Another theory that we'll talk about is an extremely important one, and that's QED, or quantum electrodynamics. Okay. So this is a theory built out of. So we're just going to consider a theory of electrons, positrons, and photons. Okay. We're not worried about other charged particles at this point. Okay? So this theory is built out of the free Lagrangian for the Dirac theory, right? The free Lagrangian for the electromagnetic field. This we haven't talked about yet. Okay, but I'll say some more about it in a minute. And then finally, we have an interaction term. Okay, so you look at this thing and you can see that we're coupling. So this is the vector bilinear that we've been talking about the past few days. We're coupling that to a field that we call A mu. Right? And this A mu is the electromagnetic vector potential, but in field theory, it's the electromagnetic field. Okay, so it's when you quantize it, the excitations of it, of this field, are photons. Right? Photons that
For the Maxwell, is that one of the four?
Yeah. And yeah. Okay. And this F mu nu, if you've had ENM2, which I guess most of you have already, hopefully you've seen the field strength tensor written in this notation. Okay. It turns out that when you write Maxwell's equations using relativistic Lorentz indices and stuff like that, you can condense them down into like two really simple looking equations. Okay?
So it's just a photon, or maybe quantized maybe it's just photon or other.
Yeah, it's just photons. Just a photon.
May I ask a question?
Sure.
F mu is tensor, but when you write it square, does it mean that you convolute it with itself into?
This is you're talking about how I've written both of them down and squared here. Yeah, it's kind of sloppy, particle physics notation. It should be really F mu nu with mu nu down, and then an F mu nu with the mu nu up. So it's two F mu nus contracted. Make sense? Okay. Yeah, it's just a shorthand notation that is confusing when you first encounter it. I remember, but you kind of get used to it and don't even think about it anymore. All right? Okay. You can be like Feynman. Feynman never kept track of contravariant and covariant indices. He just wrote everything up or everything down. Okay. So you can see,
You like Feynman?
Yeah. So be like Feynman. All right. And so this is QED. This is it. Right. This is the electromagnetic interaction. This is responsible for the forces that we observe. Most, what do I say? The most familiar force, right? That we observe. And it's crazy how simple looking it is. When you look at it, you're like, that looks like nothing, right? And it turns out that you can make it even simpler looking by introducing what's called the gauge covariant derivative. Right? So if I introduce this covariant derivative, I can write this thing in terms of two terms that look like the kinetic terms, right? For the Dirac field, except I've replaced the partial here with the covariant derivative and the kinetic term for the electromagnetic field. Okay? And so that interaction term is hidden inside of this covariant derivative. Okay? And when it's written in this form, it's easy, or I don't want to say easy, but you can show fairly easily that this thing is invariant under a transformation, particular transformation. And this is a local transformation. I think the only thing we consider a global transformation. So you notice that here the transformation parameter depends on space-time, okay? But if you, shift the field, the Dirac field like this, and at the same time shift the photon field like this, you find that the Lagrangian is invariant, okay? And so this is what's called local, like I said, a local transformation, local gauge transformation, or sometimes it's called local phase rotation of your Dirac field, okay? But that's an important point, and we'll come back to it later, okay? All right. Okay, so you can, once you have the Lagrangian, again, you can compute the equation of motion, right? Equations of motion. For the Dirac field, if you do it, you find something that looks like that, which you say, oh, I know how to solve that, but I'm here to tell you that no, you don't. Because the photon field is hidden inside that covariant derivative, okay? So it's like almost like you have a couple of equations because you can compute the equation of motion for the electromagnetic field, right? And you get something that looks like this. And I don't remember if we made a point of, I think we did, right? We talked about this thing, and we called it the current. We called it the current? Okay. Well, this thing is called the current, okay? So the Dirac field. Okay, so you can write down the equation of motion for the electromagnetic field in a very simple way, okay? And I should have noted here that, you notice this is the Dirac equation, right? But all I've done is replace partial with D, and this is something that maybe you encountered when you studied relativistic quantum mechanics. It's called minimal coupling prescription, right? So you take Dirac's equation, and if you want to couple it to a photon field, you just make that replacement. You take the partial derivative and you replace it with this thing. All right, that's called the minimal coupling prescription. Okay. All right. Okay, so we've got a theory, we've got the equations of motion. We see we can't solve them, but first you might be thinking, how are we going to work with this theory? We haven't even talked about vector fields, and in particular, we haven't talked about the electromagnetic field. Right? And it turns out that is always like one of the last topics you cover in a QFT class because it's really hard. To put it simply, it's really hard, okay? Especially in this canonical quantization way that we're doing it this semester, it turns out to be extremely difficult. And it's a little more manageable if you try to do it using path integral formalism. But in these lectures, we're going to use Jackson's first law of physics, which is if you don't know the answer, guess.
Yes.
Okay.
And
So
second thing, if you don't know, guess a Gaussian.
yeah. When in doubt, Fourier transform. I should write these down.
That's a zero.
Huh?
That's a zero.
That's a zero. Okay, so what we're going to do is basically we're going to guess. Okay, we're going to guess at the form of the propagator, and then we'll be able to guess the interaction. The interactions will be easy. It's just the propagator that you have to work at a little bit. Okay, and we'll be able to guess. We'll be able to make an educated guess because the third theory that we're going to study is called Yukawa theory. Okay, so Yukawa theory is a mix of Dirac and Klein-Gordon theories, and here you've got the free Dirac Lagrangian, the Klein-Gordon free Lagrangian, and then you have an interaction term between, say, electron, positron with this scalar field. Okay, so a lot of times, so I call this like QED, but with a scalar instead of a vector. Okay, so this theory is a lot like QED, and in fact, if you make this, so in this case, the scalar is real, but if you make the scalar complex, no, I'm thinking, never mind, I'm thinking of something else. Okay, so anyway, so this is going to be the third theory that we're going to study, and honestly, I don't know if we're going to study them in this order that I presented them, but these are the three. Okay, so if we study this, right, we know what the propagator is for the Klein-Gordon field, And it's going to lead us, using some educated guesses, we'll be able to guess the photon Feynman rules. Okay? And again, this is, you might say, oh wait, what is this good for? Well, it turns out that Yukawa used it to describe interactions of nucleons, I think, back in the 50s. But this theory has another use. It actually has a lot of uses, but one of the most important uses is it describes, or we use it to describe how the Higgs couples to fermions. Right? So in that case, this would be the Higgs, and then these would be some fermions, right? It'd be like top quarks or bottom quarks or something like that. Okay? Electrons, if you want. But that's another part of the standard model that still needs to be tested. Okay? So far, I think they've tested couplings to tau leptons, and couplings to bottom quarks, and within experimental errors, they agree with what the Yukawa Lagrangian predicts. Okay? But we don't know. There might be some surprises. Okay? Okay, so those are our three theories, all right? And this is a big question that we're going to try to answer in this lecture, okay, or start to answer it. And that is, how do we analyze the quantum mechanics of an interactive theory? Right? I've already said that, they're very hard to solve, and it turns out that, I looked this up, that there's actually no exactly solvable interacting field theory that's known in more than 2 space-time dimensions. Okay, so you have theorists out there that study these exactly solvable field theories, but they have to do it in 2 dimensions. That's as high as they can go. Okay, but there are other attempts going on with supersymmetric theories and things like that, where they are, attempting to find solvable theories. Okay? And at one point, there was a big prize that I can't remember the name of it, but if you were able to solve QCD exactly, there was some rich guy who was going to give you a bunch of money. I don't know what interest he had in it, but it's that hard. Okay, nobody won the prize. All right. Okay, so what we want to do is we're going to do what you do in quantum mechanics when you hit this kind of brick wall, which is, you run into a Hamiltonian that you don't know how to solve exactly, right? And so you try to use approximation techniques, and one of the most popular is perturbation theory, okay? And so that's what we're going to do. We're going to use perturbation theory to analyze or to try to, write down things like the propagator or interactions, and scattering amplitudes, things like that, using perturbation theory. Okay. So that's our approach. We use perturbation theory, and we basically hope that the coupling constants are small enough, in other words, less than 1, so that as you go up in perturbation theory, you're getting closer and closer to the real answer. All right, and what we're going to do is we're going to follow an analysis that was first developed by Dyson. Right, and if you guys remember, I told you that if you see Dyson's name or you see Schwinger's name, you're screwed. Okay, because they didn't do things the easy way. Okay. So what we're going to try to do is we're going to try to use what we know from quantum mechanics, non-relativistic quantum mechanics, to try to derive a space-time picture of perturbation theory. Okay? Okay, so let's look at how we're going to do this. Okay, so our goal is to develop a formalism that's going to allow us to visualize the perturbation series as space-time processes. In other words, we're trying to get to Feynman diagrams, right? And to get to Feynman diagrams, you have to shed some blood and tears. Okay, so you have to work through the nitty-gritty details. Then you earn the right to use Feynman rules. Okay. Okay. So what we're going to do is, instead of trying to tackle some complicated process, we're going to start with the what's called the 2-point correlation function. Okay, and we're going to do it in phi to the 4th theory. Okay, and so the 2-point correlation function, which we've seen in the non-interacting theory, in the interacting theory looks like this. Okay, so everything here is defined in the interacting theory. Right, so these omegas are the ground state in the interacting theory. Right, and the fields are obviously in the interacting theory. Okay, and in general, that ground state is going to be different in the interacting theory than it is in the free theory. And that you would expect, right, from even if you just know a little bit of quantum mechanics. And T, just to remind you, is the time ordering operator. Okay, it's going to come in and play an important role. Okay. And so the correlation function, again, remember it's related to the propagator, right? It gives you the probability or the amplitude for a particle, that's created at one space-time point to propagate to another space-time point. Okay, and from that we extract the propagator. Okay. And we computed this. It's been a long time ago now, it seems like, but for the free theory, the free Klein-Gordon theory. And remember that when we did it, we called this thing the Feynman propagator, and it took that form. Okay, and in position space. And in momentum space, it takes a much simpler form, but this is what we derived. I don't know. Back in the olden days, I don't remember how long ago it was.
Summer.
Well, yeah, no, this semester. Yeah. Okay. So what do we want to do? We want to compute this thing, right? And we're going to treat the interaction, the phi to the 4th interaction, as a perturbation. Okay. So what we want to ask is, how is this expression that we have for the propagator, how is it going to change once we include interactions? And to answer that, what we're going to do is use the ideas of perturbation theory. In perturbation theory, when you start with a Hamiltonian, the idea is to break it into what I call a simple piece and a small piece. Okay? The simple piece means that you know the solution for it. Okay? So in this case, for us, it's going to be the free Klein-Gordon theory or the free Dirac Lagrange, right? And the small piece are going to be the interactions. Okay? So the small piece for us and this phi to the 4th theory is going to be the phi to the 4th term. Okay? And again, like what we want to do is we want to compute this thing. I'm just going to call it the propagator. We're going to compute the propagator in this interacting theory. We're going to do it using perturbation theory, and so we're going to end up with a power series, right? And the hope is that this coupling is small enough that that the higher order terms in the power series get smaller and smaller. Okay? All right. So to do that, to start, you first have to identify places where the Hamiltonian, this thing, where it appears, right? And it appears in two places. Right? It appears in the operators, the fields, right? Because we're working in the Heisenberg picture. Okay, so remember, Heisenberg picture operators evolve with time, or in field theory, the fields evolve with time. Right? And it appears like this. So this is just a general, way of writing the Heisenberg operator. Right? We sandwich it between two time evolution operators. Hopefully this sounds familiar. Okay, and the Hamiltonian also comes in the definition of the ground state in the interacting theory. Okay, and so what we want to do is we want to try to take these things and write them in terms of stuff that we know how to work with, right? Which are free field operators and free theory vacuum. Right? So I want to replace everywhere I have here these things. I want to try to write those things in terms of the free fields, right? And the vacuum, I want to write it in terms of the free theory vacuum, okay? And what we'll find is that we can expand these things in a perturbative series, both of them, and come up with an approximate answer for this thing. Okay? All right, so to do that, let's start with the field in the interacting theory. Okay? And so the field in the interacting theory at some particular time, which is P naught, okay? And it has the same type of solution, okay? So it's got the same, we can still do this Fourier expansion, right? In terms of A and A daggers, right? And this same type of form that we're used to, okay? And then what we want to do is we want the field at some general time, right? The way we do that is we evolve in time using time evolution operators. Okay, so we want to take this thing at some particular T naught and sandwich it between two time evolution operators. Okay, so we're going to be working in the Heisenberg picture, and that's the picture that you work in 99% of the time in quantum field theory. Okay? So first, it's important to identify that when I turn off the interaction, the Hamiltonian for the interacting theory just becomes the Hamiltonian of free theory, right? And in that case, I would write down something like this, right? But this is just the Heisenberg picture operator in the free theory, right? Okay, so I'm just taking once I take H to H naught, then everything here is non-interacting theory, right? The free theory. Okay, and so we're going to define that thing when the H's are H naught. We're going to define that thing as phi I. Okay, the I subscript confuses me because you would think that would mean interacting, right? But it's not. It's the field and the non-interacting. I just didn't have the nerve to change Peskin's notation, okay? He's a pretty intimidating dude, if you ever meet him. Okay. All right, and so our hope is, using this perturbative expansion that when we solve for the true interacting theory field, right, that this thing, the piece that comes from H naught time evolution, is going to be the most important piece, right? And the pieces that we get when we add back in the interacting terms are going to be small perturbations on that. Okay, so we're going to work under that assumption. Okay, and so I guess so here's where the I comes in. It's called the interaction picture field. And the interaction picture, I don't know, if you run into it when you study scattering theory. So you know that there's the Schrödinger picture and the Heisenberg picture of time evolution, right? But there's also this interaction picture, right, where it's kind of a mix between the two, right? It's because the operators evolve with time, but the states also evolve with time, right? It's one of those cases where you define a picture that makes your life simpler, right? And it turns out that in this interaction picture, scattering, computing scattering processes is a lot easier. Okay. So in this case, where we turned off the interaction, we know that we know the solutions for this thing, right? And we can write a general solution for our interaction picture field like this, right? We've written this. We've written this a million times, right? And you say this looks exactly like this guy, right? But it's supposed to be the time evolved state, the time evolved field, right? And that's because what we've done is we've kind of hidden the time dependence by replacing x naught, so the x that appears in these dot products, with t minus t naught. Okay, so this is like propagating it, right? The t minus t naught is the time of propagation, I guess. Okay. So we're working with an expression that it looks familiar, and we feel comfortable with it, right? But it's been time evolved. Okay. All right. So now we've got our our free field, field, okay?
Can I ask a question?
Yeah,
So we assume that H and H0 are not commute. Do not commute, right? Two Hamiltonians, perturbated and non-perturbated.
we haven't assumed anything yet about their.
How we can separate it?
Well, they're just, I mean, it's just it's just, you mean, where do you
How
mean
we can
separate?
separate exponent?
Mhm.
Maybe he means separating the simple piece from the small piece.
Is that what you mean? Or I don't know which.
Yeah, that we split it one exponent with sum of Hamiltonians into two.
Yeah, I mean, that's you know, the basis, that's where you start in perturbation theory, right? You have an interaction or you know, a system that's described by a Hamiltonian that has, you know, a familiar form, piece that you know how to solve. So say it's like, you know, the simple harmonic oscillator, right? And then say you add in some perturbation that goes like x to the fourth, right? So that term doesn't necessarily commute with the H naught. It probably doesn't, right? But you're able to split it off. Okay, so you solve the, you know, the system that you know, which is the simple harmonic oscillator, and then in that case, the x to the fourth term would be a small perturbation, right? That you would apply perturbation theory to. Does that help?
Yeah, but then probably I don't understand why we wrote it finally. So we have initial state, we propagate our initial state with our like H0
Yeah.
Hamiltonian, and after that we propagate it backwards. Why do we have different signs?
You propagate it. Oh, you're talking about this expression?
Yeah.
I'm
Why
getting.
do we have different signs?
Yeah. Oh, no. Yeah. So you're talking about the different signs between here
Mhm.
and here.
Yeah.
Yeah. Yeah, I thought about that. Let me remember what I came up with. Oh, I remember what I came up with. Because here, okay, so this is the field at one instant of time, right?
Mm-hmm.
And then we time evolve it, okay? And we got this
Mhm.
phi I. But you notice here is phi I, right? So what I'm doing, so what I'm doing is canceling off these two guys because I want, you know, I want something that looks like this for the interactive field.
Mm-hmm.
That makes sense now?
Yeah, and at the initial moment of time, we think that system in non-perturbed state, right?
What, I missed the first part.
Initial moment system is without perturbation.
Yeah. Yes. The phi interaction, the interaction picture phi? Yeah. That's without perturbation. Okay. Okay. So now what we want to do, like I said, is we want to express the full Heisenberg field. In other words, the field that, you know, feels the interactions in terms of phi I. Right? So phi I is the thing that we know how to work with, right? We know what its solutions look like. I just had them on the bottom of that last page. Okay, so we want to write this guy a time evolved state for the full Heisenberg field. Right? And so, like I said, we can write it in terms of phi I, but you know, I have to cancel. Technically, I have to cancel those the exponentials, the time evolution operators that are inside this phi I. So that's the reason for these two guys. Okay, and then we sandwich it between the two time evolution operators for the full theory. Note that these H's don't have a subscript. Okay, so these are the full theories. All right, and so what I can do is I can define these things, the combination of these exponentials, as some unitary operator, right? So this is our time evolution operator in the interacting theory, okay? Right, here's where I define it, okay? So it's just defined like this. Okay. All right, so what is this thing? Well, if you recall, if you study quantum mechanics from Sakurai, you know that this time evolution operator is the solution to the Schrodinger equation, right? The Schrodinger-like equation. Okay. So what I've done here is written down that equation. Okay. And here I'm not assuming anything about H or H naught, so that's why they appear on opposite sides. Okay. But H minus H naught inside of here is just the interaction term. All right. And then what I can do is insert 1. Where am I inserting 1? This must be a H naught. Yeah. So I'm inserting 1 here, so this is 1, right? And what I get is these 3 terms give me interaction picture Hamiltonian, and these 2 terms give me the time evolution operator. Okay? So I have a nice little differential equation that I can solve for our time evolution operator. And I've just defined the interaction picture Hamiltonian. So this is the interaction piece, right? Here. Right? And if you remember, and this is starting to ring bells in my head, in the interaction picture, the idea is to strip off all the stuff that you know how to solve, right? Just to get rid of it so you don't have to keep carrying it through the calculation, okay? Look back at Sakurai, you'll see what I'm talking about, okay? But anyways, so that's what we're doing here. We're stripping off the pieces that we know how to solve and we don't really care about. We're trying to get to the interacting pieces. Okay? All right. So what I have is the interaction Hamiltonian. It looks like this. Okay? And it's in terms. Note that it's in terms of my interaction picture field. Right. That's important because that's what we're trying to get to. We're trying to get to things that are written in terms of phi I, which we know the solutions for, and the ground state of the non-interacting theory. Okay. All right, so you look at this differential equation, right, and you know how to solve this thing. You just separate and integrate, and so you expect that you get something that looks like this. Okay, this thing here. Right, that would be the normal case. Right? But unfortunately, you'll run into cases where the Lagrangian, or not, the Hamiltonian at different times doesn't necessarily commute with itself. Okay, so there's a more general solution, and you touch on it in quantum mechanics, but it's called the Dyson series. Okay, and I call it the dreaded Dyson series. Okay, so this is what the general solution looks like. Okay, so you can see that it almost looks like an exponential, right? But the fact that you have these h's at different times, right, and you're integrating over them, makes it difficult. Okay, these are in time order, right? H1, H2, H3. We're assuming some time ordering here, right? We're say T1 is less than T2 and T2 is less than T3 in the way that we've written it. Okay, so that can simplify your life, right? Because what you can do is you can throw in your time ordering operator, right, and rewrite something that looks like this in this way, right? And it basically looks the same, but what this thing is telling you is that you're considering, you've got things in the right time order, okay? And you can do it for all the terms, right? And you can, it condenses all of these higher order terms that I didn't want to write down. But what you get is something that looks like this, right? And now you see that this is really starting to look like an exponential, right? If I'm assuming that with each power of hi, the terms are getting smaller and smaller, right? And if that's the case, then I can write this propagator in kind of a shorthand notation where I pull out the time ordering operator and I write the series as an exponential. Okay? It's a little deceiving because really what you work with is this thing. Okay? You work with the expansion, right? But as a shorthand notation, like I say, you can write that as the exponential, but just know that you're always going to be expanding that exponential. Right? Okay. All right. So now we have. Let's go back. To where it was. All right. So we have the Hamiltonian, right, in terms of phi I, which we know how to deal with, and now we know how to solve this differential equation. We know what U is. All right, so if I need to propagate with time, I just hit the Hamiltonian here. Okay. Yeah. So we've got our field, our interacting field. We've got it written in terms of the basically the free field. Okay. And so now what we need to do is work on this ground state energy, right? This ground state for the interacting theory. Okay, so let's do that. Let's consider this ground state. Okay? And this is like I said, this is the ground state of the full theory, right? The full interacting theory. Okay, and the way that you handle this is through kind of a procedure, and you guys in the summer saw this, but let me go through it again. Okay, so let's start with the true ground state, the ground state of the free theory. Right, we're working under the assumption that that's going to be a good approximation to the interacting ground state, right? And anything else is going to be a small perturbation. Okay? And let's take that ground state and time evolve it. Okay? But time evolve it with the full interacting Hamiltonian. Okay? So this guy, the 0 here, is not an eigenkette of this guy. Right? This is an eigenkette of H naught. Okay? So what I need to do is insert a complete set of eigenstates for this Hamiltonian, for the interacting Hamiltonian, right? So that I can evaluate this exponential. Okay? So that's what I do. So I insert this complete set of states, which I denote by n, right? And then I'm allowed to hit those states with this exponential, and it gives me the eigenvalue e sub n. Right? Okay. All right. So again, like I said, we're assuming that our interacting ground state has some overlap with the non-interacting ground state, right? And that's it has to have more than just some. It's going to have quite a bit, right? Because if it doesn't, just think about if it was say it was orthogonal to the ground state, then perturbation theory is completely shot, right? Because you've changed the ground state, by as much as you can change it, basically, right? Okay. So we're going to assume that it has overlap. Okay. And like I said, if it wasn't the case, then we wouldn't be dealing with small perturbations. We'd be dealing with large effects. Okay. Okay. So let me, working under that assumption, that means that, in the sum over these eigenstates, I'm going to hit one term where n is equal to this interacting ground state thing. Right? And in that case, this E sub n is going to be the 0 energy, right? The ground state energy of this interacting ground state. Okay? And then I've got the rest of the terms over here where I've got n can't be 0. Okay? And then by assumption, the energies for n not equal to 0 are all going to be greater than the ground state energy. Okay? So what that means is we can get rid of these terms by using a little trick. And it seems like a big trick. It seems mysterious, but you'll see how it comes, the true power of it, I guess, later on. But let's just assume that we can do this, okay? And the way we're going to do it is we're going to take t to infinity. All right? We're going to take t, the time here, and the time evolution operator. We're going to take it to infinity. But we're not going to do it, just straight to infinity. We're going to do it kind of slightly skewed into the complex plane. Okay? So I'm going to take t to infinity plus some small imaginary piece. Okay? All right? And so what does that mean? So it means that if I look at one of these terms, say I look at the nth term, right? And then I take this limit of t goes to infinity, right? So t goes to infinity inside of here, right? Well, what happens is if I do it slightly skewed into the complex plane, this term combines with this minus I out here, right? And it gives me an exponentially decaying exponential, right? In addition to the oscillating piece. Okay? So what that means is that when I go to infinity, these guys, for n not equal to 0, are going to die off faster than the n equals 0 term. Okay? Does that make sense? Right? Everybody good with that?
So
So,
What's that?
I got side this on there.
Yeah. Yeah, it's the same trick. Yeah. Okay. All right, so in the end, what it's telling us is that I can get rid of all of these terms because I'm taking this limit of t goes to infinity plus some complex piece. Okay? And all that's left is the ground state piece. So all that's left out of that stuff is this thing, and now I can solve for this guy. So these are just some numbers here. Right? So I can divide them through and solve for the interacting ground state energy. Okay? It's ugly, right? It's got this weird looking prefactor, okay? But it's what we want. It's an expression for the interacting ground state in terms of the non-interacting ground state. Okay? All right, so here we're going to use another trick, okay? So now, since t is very large, we're taking it to infinity. If we shift it by some small amount, it's not going to make a big difference, right? So what I'm going to do is shift t to be to have some additional little t naught term. Okay, so everywhere I have t, I replace with t plus t naught. Okay. All right. Okay. So we've got this, right? And now I'm going to use another trick where I use the fact that I know that h naught when it hits the ground state gives me 0. Okay, how does that help me? Well, it lets me introduce another exponential here between this guy and the ground state. Right? I can introduce an exponential that goes like h naught, right? Because I know when this hits this, it gives me 0, and so this term will just give me 1. Okay? And then what I see is that these two terms combined, they're of the form of our time evolution operator, right? From some time minus t to t naught. Okay? And then I've got this, again, this prefactor. Right? But if we ignore it, it's telling us that we can get this interacting ground state from the non-interacting ground state by using a time evolution operator, right? And evolving from minus t to some t naught. Okay? Mm-hmm. Yeah, because remember, so we're taking t to infinity here, so this is like, I don't want to spoil it. Okay? All right. I don't want to spoil that yet. Okay. All right. Yeah, so it's just on time. Okay, that's large and negative. And it rhymes with schminfinity. Okay, don't worry about it. All right? Okay. And you can go through the same exercise and get the bra, right? The bra just looks the same way, okay? Except the time evolution operator takes this, slightly different form. Okay, but now we've got this, right, and we've got expressions for our field in terms of the phi I field, right, in terms of the interacting field. So we're finally in a position. We're finally in a position to compute this thing. Okay? This is what we started out to compute. 2-point correlation function and their interacting theory. Right? All this work was to get these fields in terms of the non-interacting field, and these guys in terms of the non-interacting vacuum. And now we've done it. Okay? It's ugly as hell, but let's see if we can pretty it up a little bit. Okay? So we can build this thing. All right? So for the time being, let's just assume that x naught is greater than y naught is greater than whatever this t naught is. Okay? So I'm going to construct this thing, right? And we know that we're taking the limit of t goes to infinity plus some small complex piece for these guys, for the bras and the cats. Okay? So this first line is the bra, this guy. Okay? This middle stuff here, right, are the fields, right? Because we saw that we could write phi, and in terms of phi I, with sandwiched between some time evolution operators. And I made sure to keep the arguments straight. Okay? And then here's the cat. Okay? And when you scrunch all that stuff together, you multiply it through, you see that the prefactor condenses down to this. The T naught terms cancel out. So that's a good thing, because that was a shift that we put in. Right? So that cancels out. Okay? And what you see is what you have left is this thing times this. Okay? And we can actually get rid of this by dividing by 1. Right? In terms of writing 1 as the inner product, or the inner product of the interacting ground state with itself. And if you go through and you plug in our expressions, you find that you get something like this, right? And this is the same prefactor that you have. So we're basically normalizing, the correlation function. Okay? And so if I divide through by that, I end up with this thing. Okay? So this is starting to look a little more manageable. Right? Pascal calls it simple. I won't call that thing simple. Okay? But it's starting to look better, right? So we just have to remember to take this limit, but we've got everything now in terms of stuff that we know. Right? And this is for one particular time order. Right? So if you want to put it back in the time ordering operator, right? So that the times are arbitrary, right? Then we can get this expression in the double box. And what I've done is plugged in for the u's. So plugged in u in terms of these intervals. Okay? And so what we get for the time ordered product of two fields of the correlation function is this thing. Okay? This is the final answer. And it turns out that this expression is exact so far. We haven't done anything with perturbation theory yet. Okay? All we've done is basically separated out, the interaction piece, right, from the non-interacting fields. Okay? All right, so that's what I'm going to stop there, okay, for today. And then when we pick it up next time, we're going to start to investigate how we apply perturbation theory to this. Okay, so we'll use perturbation theory to compute the propagator. Okay? Any questions or comments, concerns?
This expression is the interacting?
This is the propagator and the interacting.
Unperturbed? Unperturbed?
Yeah, this is the exact expression. Yeah, we'll apply perturbation theory by basically expanding that exponential, right?
Okay.
That contains our.
Yeah. Okay.
Yeah, this is the full thing right now.
Okay.
Right? So what we have to do now is expand it so that we can solve it.
So this is equivalent to like H. where in like say point two, and then where that equals the simple piece plus the small piece.
Yeah.
This is the
Yeah, this is, yeah, that's, yeah, so this is the full thing. Okay, all right. Okay, see you guys Wednesday.
See you.
I think you missed a closed parentheses between the cat at the end and the curly brace on the exponent, the denominator. Maybe should be outside the brace. Or no, that's right.
Yeah.
You're right.
I think we skipped the part that we proved actually that this wave function describes this field describes the area. This one based on regular.
When did I say it was gonna do that?
Before you said we're gonna see a couple of lectures.
Oh.
We prove that this is basic. This is actually describing this.
Yeah, I guess I forgot that I said that. I'll try to,
Just saying.
yeah, no, I think I remember saying that now, but I'll try to work it in. There's a nice, well, that's not really what you're asking. I was gonna say the spin statistics theorem, which relates the spin, of the particle. It's statistics, but that's not really what you're asking. You're asking proof of that. It's a direct equation that describes a spin one-half particle.
Like it's in quantum, we just put it by hand. There's one part we put it by hand next to angular momentum without explanation of why we can do that. But in field theory, we can actually obtain this. Sure.
Yeah, I don't know. I have to think about it.